When you watch an AI type out a response, the smooth flow of text on the screen creates a compelling illusion. It feels as though the system has conceived the entire paragraph at once and is simply transcribing its thoughts. The reality is much narrower. Modern language models operate entirely on a principle called auto-regression. Despite utilizing thousands of GPUs and billions of parameters, the model's absolute maximum capacity in a single computation cycle is calculating the statistical probability of exactly one subsequent token. The core mechanism is a loop. The engine generates that single token, appends it to the end of your original prompt, and then forces the entire newly expanded text sequence back through the system from scratch. To understand how these models actually process language, we have to stop looking at the final, human-readable paragraphs. We need to freeze time and analyze the discrete state transformations that occur inside just one micro-iteration of the cycle. This system flowchart outlines the complete path of that micro-iteration, from tokenization to sampling. The architecture is built to solve a basic incompatibility. Neural networks require continuous, geometric mathematical data to function. Human language, however, is made of discrete categorical symbols, words, and punctuation. The first half of this pipeline operates as a translator, converting those discrete linguistic symbols into a continuous mathematical format that the core engine can ingest. Once the computations are complete, the second half of the pipeline reverses the process, mapping that dense geometry back into a discrete probability distribution. The entire architecture is a rigid assembly line. It converts meaning into geometry, performs a transformation, and translates the geometry back into a vocabulary choice. The process starts here, at tokenization. Raw strings of text cannot be computed directly. Before the math can begin, words, spaces, and punctuation marks must be sliced into standardized subword units. The system references a hard-coded vocabulary dictionary, matching these sliced text chunks to specific assigned integer IDs. Through this initial transformation, your human-readable prompt becomes a simple, one-dimensional array of atomic integers. At this exact stage, these integers carry zero semantic weight. They hold no grammatical rules or definitions. They are strictly database lookup keys. Tokenization strips language of context, reducing human expression to the sterile data structure required to enter the model. Those sterile keys move to the embedding stage, where mathematical meaning is applied for the first time. Because simple integers cannot interact to form grammatical relationships, the system must translate them into a format that allows for computation. The model looks up each integer ID and replaces it with a dense, high-dimensional continuous vector. In this vector space, geometry equals meaning. The physical distance and direction between points correlate directly to their semantic similarity. The data payload has drastically changed state. What entered as a flat line of discrete integers expands into a massive, dense matrix of floating point numbers. The embedding layer creates a geometric map of semantic relationships, ensuring the text is finally susceptible to mathematical manipulation. This expanded matrix now hits the core computational engine, the transformer block. The embedding vectors arriving here are static. They contain isolated dictionary definitions, but they have no awareness of the surrounding sentence structure. To solve this lack of context, the model applies the self-attention mechanism. Self-attention allows the model to simultaneously weigh the relevance of every token in the sequence against every other token. The system uses these computed attention weights to mathematically update and shift the coordinates of the original embedding vectors. For example, the vector for the word bank will shift its physical location in the space dramatically, depending on whether the attention weights prioritize the surrounding word river or the word money. This is an operation of immense scale. The model executes billions of parameters and vast matrix multiplications across successive layers to finalize these coordinates. The output state of the transformer block is a highly enriched, context-aware matrix that represents the full semantic weight of your prompt. Crucially, the trajectory of this final matrix points geometrically toward the statistical space of the next logical vector in the sequence. The transformer's vast geometric transformations take static dictionary definitions and warp them into a complex map of contextual relationships. With the context established, the system must exit the continuous mathematical space. The transformer outputs what are known as logits. These are raw, unnormalized prediction scores for every single possible token in the model's entire vocabulary. To make these scores usable, the model passes them through a softmax function. The softmax operation squashes those unbounded logits, forcing them into a normalized probability distribution that mathematically sums to exactly 100%. Physically, this distribution is a ranked list. It details the exact mathematical likelihood of every known word being the correct next piece of the sequence. The dense, continuous geometry processed by the transformer has now been translated back into an actionable list of discrete vocabulary choices. We arrive at the final stage of the forward pass, sampling. You might assume the model looks at that probability distribution and simply outputs the single highest-ranked word. However, always choosing the most probable token, a method called greedy decoding, frequently traps the model. Without any randomness, the system often falls into high-probability generic patterns that eventually feed back into themselves, creating repetitive loops. Instead, the system introduces controlled stochasticity. It effectively rolls a loaded die, heavily weighted by the probability distribution, to select the winning token. This sampling phase introduces mechanical variance. It is the exact reason why submitting the identical prompt will generate a slightly different creative text sequence every time. The system has finally produced a single, discrete token. This isolated token is immediately appended to the end of your original input text. This entire pipeline, the slicing of text, the mapping to vectors, the heavy matrix multiplications, the probability distributions, executed purely to generate a fraction of a single word. With the sequence now lengthened by one token, the loop fires again, repeating the identical chain of state transformations. The illusion of a coherent response is built on this rapid mathematical cycle, a relentless translation between language and geometry that repeats hundreds of times a second.